Hello, space fans, and welcome to this week's Afternoon Astronomy Coffee Hangout. My name is Deep Astronomy. I'm with TonyDarnell.com. Reverse that. Tony Darnell with deepastronomy.com. And today we are going to be talking about stars moving around in space very quickly, very big stars moving around in the galaxy very quickly, creating bow shocks. And we're also going to talk about some citizen science that my guests have set up to help you get involved. It's called the Milky Way Project.org, and we're going to be giving you some previews of that, and you can follow along as we do our hangout as well. So we hope you will enjoy that. With me, as she is every week, is my esteemed friend and colleague, Dr. Carol Christian from the Center for Emerging Media. And welcome, Carol. It's good to see you again.
Hi, it's good to see
each other all that much, do we, these days?
I know, and I was just in Florida, so yeah, I was even closer to you, but you know, it was just busy, crazy.
I know.
And windy. It was windy.
I know. Oops,
yes.
Somebody just went away.
One
of our guests popped out. Hopefully he'll pop back in soon. Okay, so as I mentioned, so these hangouts, I'm going to have Carol go into this just a little bit more, are something that we put together to sort of get you guys joined in with the spirit of what astronomers do every week. Carol, do you want to expand on that a little bit?
Yeah, sorry, I couldn't find my mute button.
That's all right.
Yes. So astronomers and scientists in general, we often in our departments and research organizations have something called Science Coffee. In my organization at Space Telescope, which is my formal organization where I'm gainfully employed, we have something called Science Coffee. We actually have a daily one, but the big one is on Friday. And the idea is people get together and bring a cup of coffee, and we often discuss research results that we've read about. And it could be any topic that strikes somebody. And we were talking about this among ourselves with our colleagues, you know, with Tony and with Alberto Conti and with Harley Thronson, who do Footsteps to Mars and Future in Space. And we said, you know, we should do an afternoon coffee, but instead of us sitting around and just yakking about somebody else's work, why don't we let somebody else talk about the work that we do? And then we'll have a nice chat about it. So it's very informal. It's not like a press release. It's not like a colloquium where everybody throws daggers at you. It's just an informal chat to see how this research came about, what happened, what was found. And that's why it's called Afternoon Astronomy Coffee.
That's right. And we want to get you guys involved because this is a live event. And there's no point in us just talking amongst ourselves. Well, you can join in as well. And there's three ways you can do it. The first way is on YouTube. I've got the live chat client going. Andrew Planet has joined us, and he's on vacation, by the way, which is and so he's here chilling on vacation watching, and he's got his question. I'm going to get to it, Andrew, I promise. And you can also interact on deepastronomy.com/live, where I have a separate live chat client going. But you know what, guys, I have been so pleased with how the YouTube live chat client has changed. I may not do this in the future because I built this because it just seemed like the live chat on YouTube was too crazy and I couldn't control it all. But this gotten a lot better, so I may just use it exclusively starting next week. But we'll see how it goes. And finally, on Twitter, we have the hashtag AstroCoffee, and you can interact that way. So please leave our questions for our guests and comments. Carol, you want to say something about the AASs?
Yes, I did. So the American Astronomical Society supports this. This is our professional society for astronomers. They've been very interested in this in a way to get the word out about what the astronomy community is doing. We, of course, have our own meetings where we all talk about the research. We have meetings twice a year and then topical meetings. But this is our opportunity to talk to you and interact with you about the astronomy that we do. And another organization which is also providing endorsement and support is the American Astronautical Society. And that's really the society that supports a lot of engineers that work in the space industry. So we thank both AASs for their support and endorsement.
So we got you folks from every angle. So we want to thank both these organizations for helping us get the word out. Okay, so let's get started. I wanted to just mention real quick that while the Hangouts are endorsed by those organizations, the views and opinions expressed in these Hangouts are not necessarily endorsed, especially mine or Carol's. But anyway, okay, so let's get to our guests. My guests today are these two. Our first two guests are from the California State Polytechnic University, or Cal Poly in Pomona, California. Dr. Matt Povich, he's the lead scientist of the Milky Way project, and he's an assistant professor of physics and astronomy there. Hi, Matthew, welcome. And also joining right next to him on his right is Don Dixon. He is an undergraduate there. I presumably you work with Dr. Povich, and he's here to talk about his role and his involvement in this project. So welcome. It's good to have you here, Don. Also, later in the hangout, I might ask for your opinion on what you think how you like studying physics. Or are you a physics major or astronomy major?
Well, at Cal Poly, they don't have astronomy major, so I am a physics major.
Oh, you're a physics major. Good. Okay, good. Yeah, they didn't at CU when I went there either. They added that while I was there, so that was not all institutions do it. Okay. Also joining me is Dr. Will Chick. I'm sorry, Will Chick. He is a grad student. He's on his way to becoming Dr. Will.
Not quite there yet.
Right, and he is right in the middle of the country at the University of Wyoming. So welcome, Chick.
Well, thank you for having me.
Okay, so let's talk about the paper. Now, by the way, folks, if you want to see the paper, I've got a link to both the AAS Nova link to this paper as well as the Astro PH link to the paper itself. So feel free to follow along while we're talking about it. And let's see. I think I'll start. Why don't I start with you, Matthew? Give us a little background on what this paper is about. We'll just give us an overall idea what your research is here.
Okay, well, we were, so this paper actually started out of a collaboration between Will's PhD thesis advisor, Dr. Chip Kobelnicki, who wasn't able to join us today. And, Chip and I have known each other for quite a few years. And we're both members of the GLIMPSE collaboration that used Spitzer Space Telescope to survey the whole Milky Way galaxy's plane, and that's sort of how we got to know each other working in that larger collaboration. And he approached me with this idea to study these objects called stellar wind bow shocks that we observe in the infrared, and obviously we'll talk later about what exactly that means. And I'd done a paper presenting a few of these, like 6 possible candidates in 2 different star-forming nebulae. That was part of my PhD thesis. Chip, a couple years later, had done a rather, at least at the time, seemingly exhaustive survey of the Cygnus X star-forming region looking for these. He found about a dozen candidates. He said, hey, what if we get together and try to look for them throughout the galaxy and see how many we can find. And if we find enough of them, we might be able to say something about stellar winds and mass loss rates from the most powerful stars there are.
Okay. So
that's sort of how things got going, and we wrote a grant together to the National Science Foundation, and we were fortunate enough that it was funded. This was back in September of 2015, I think, or was it 2014? It's been a few years ago that it started up.
Okay. All right. Good. Well, thank you for that. So. Folks, this topic, before I get too far down on this, I want to sort of take a step back and get some of the basics in. We're talking about very fast stars. And now we all know that the stars move within the Milky Way and they follow an overall pattern, but some stars are moving slower than others. Some stars are moving faster than others. And what we're talking about here today, and you guys correct me if I'm wrong, if I say anything incorrectly, very fast moving, massive stars, right? Okay, so all right. So, Will, how massive are we talking about here?
Generally, we're talking about stars that are in the O or B spectral types. So we're talking about stars that are 8 or much more massive, up to even 80 solar masses. So 80 times the mass of our sun.
So anywhere from
we're getting
8 to 80 solar masses.
Yep, give or take. That's about right.
Okay, and so when these stars travel through the galaxy, they are traveling through something called the interstellar medium, which we all know that the vacuum of space is not purely a vacuum. There's still stuff in there. There's still particles and atoms and molecules, still dust and grains like that, still in the interstellar medium. And when these stars go fast enough that they go supersonic, they create these bow waves. Now, one question that I always get when we talk about space and sound speeds in space is the question, how can you have sound speeds in space? There is no sound in space, but that's not exactly true. If you think about a jet fighter going through the Earth's atmosphere, if it goes fast enough, it will create a sonic boom, which is similar to the bow shock that we're talking about here. And analogous to that is if you've got a fast-moving star, a very large one, moving through the interstellar medium, it's actually not moving through completely empty space. It's moving through atoms and a very sparsely populated interstellar medium, but it can create, there's a sound speed to that medium as well. And the sound speed, or the acoustic speed, is based on the density of the gas that it's traveling through. And it will be very different. So obviously, for a very dense atmosphere, like comparatively dense atmosphere like the Earth, it would be a lower sound speed than for something that would be very, very diffuse. So when we talk about sound speeds, it's different for the medium we're talking about. The solar corona has a sound speed. The Earth's atmosphere has a sound speed. A supersonic speed, and so does the interstellar medium. And that's what we're talking about here. And I wanted to kind of clarify that because these bow shocks are a result of these huge stars moving through this interstellar medium. So maybe, Will, can you give us some sense of how big are these bow shocks, by the way? Do we know how big they are?
We're trying to pin that down exactly right now, but on general, we're talking about something that's going to be on the order of multiple astronomical units, so the distance from the Earth to the Sun, to possibly even as much as maybe even a light year across for the very largest stars traveling through the densest material.
Okay, and what? And I did not get a chance, unfortunately, to download the AstroPH paper to see. But what wavelengths were we talking about here that you observed these in? What kind of telescopes did you look at?
Well, these nebulae are made up of shocked gas and dust from the interstellar medium. So we're talking about warm dust on the order of maybe 200 or 300 degrees Kelvin. So roughly the temperature of the Earth's atmosphere to what you would see in the coldest day in Antarctica. So this only radiates in the infrared. So we're talking about dust that's radiating at about 12 and 24 microns, which is why these infrared telescopes like Spitzer are so keen seeing these nebulae.
Okay, so I take it Spitzer was one you looked at.
That's correct.
Okay, so this is a schematic you guys sent me on one of the sort of outlines what a bow shock is. Does somebody want to describe this to me? Oh wait, what do you got up there, Matt?
I was thinking we might start with the picture of the actual thing, and then
let's do that then. I've got you big. Go right ahead.
Okay, let me get me big. All right, so so this is like everybody's favorite bow shock in the infrared. This has been a press release from the WISE telescope, the Wide Field Infrared Survey Explorer. This is one of the most nearby examples of a massive runaway star to the sun. You know, these things aren't very common, so there aren't very many that are relatively close to us. But this one, I don't know exactly how far away, but we're talking something measured in hundreds of light years instead of thousands. So that's pretty close by. And this thing looks enormous on the sky. So these are the infrared wavelengths that we were talking about. The green is about 12 microns. So that's 12 millionths of a meter wavelength. And then the red is 21 microns. And then you see the star in the middle, that shows up more in blue. That's about 3 or 4 microns. All right, so this is all infrared.
Yeah.
The analogy we like to make, and you've said already that there's an interstellar medium, that's gas and dust that permeates space between all of the stars in our galaxy. And when a star like this is moving quickly, well, it's not just the star. The star is blowing out something called a stellar wind. The stellar wind it's analogous to the solar wind, but it's much more powerful. This is a stream of highly charged particles that are being cast off from the outer atmosphere of the sun and accelerated out into space. A wind from a star like this can reach 1,000 to 2,000 kilometers per second in speed. And that wind kind of makes a big bubble around the star, and where that wind runs into the interstellar medium in the direction of motion, you get this pileup, and it is analogous to that shock wave that makes the sonic boom from a fighter aircraft. But we like to call them bow shocks because they're softer. They're not V-shaped. They're nice and curvy shaped. So in this picture, we would say that the star is moving like a ship through the water, but the star isn't the ship. What's the star, Don?
The star is the engine of the ship, so it powers the bow shock.
Right, and then the ship itself isn't the star; it's the wind of the star in this analogy. And then the surrounding ocean is the surrounding gas and dust in space that gets piled up by the wind and makes this bow wave.
And so, as Will was saying, these are like a couple of AU across.
Oh, a lot more than that. Thousands of astronomical units across.
Okay.
Up to like Will said, a good fraction of a light year. We're still working on measuring them all.
Is there a limit to the kinds of stars? Are these a feature of fast-moving massive stars only? Do you need to have a large stellar wind to have this built up, or will smaller stars make them too? You just can't see them as much.
Smaller stars make them too, but we can't see them as much.
Okay.
Or at all.
Or at all. Okay.
Yeah.
So good infrared telescopes like Spitzer help us get these observations. So your picture is better than mine, but I'm going to go ahead and put this back up again on the schematic just to kind of see a little bit more the nature of it. So we have the star itself, like you said, which is more of the engine, and then I didn't consider there's a stellar wind coming out also in all directions from the star that's kind of blasting up against the interstellar medium. Now it strikes me that if you're seeing one of these going really bright in some areas of the galaxy, the interstellar medium is not going to be as prevalent as in other parts of the galaxy, right? Is there any kind of neighborhood in our galaxy where we're more likely to see these things?
We're much more likely to see these within the plane of the galaxy where all that gas and dust tends to be concentrated. However, these massive stars that we're talking about, because they're so short-lived, they also tend to be concentrated within the plane of the galaxy itself. These are stars that live tens or hundreds of million years as opposed to the 10 billion years that our sun will live. So they just don't have a whole lot of time to get far away from the plane of the galaxy themselves. So they're kind of overlapping scale heights on these two, the gas and the stars themselves.
Yeah, well, it's interesting though, because given we think these are fast movers, and again, we're talking 100 kilometers per second, even in 10 or 20 million years, you can get pretty far. You know, a star can get pretty far moving that quickly. And, you know, this is in our paper where this distribution of where the bow shocks are above and below the galaxy, and I was initially surprised they were as close as they were. They really do look like the distribution of massive stars generally, not necessarily just the fast moving ones. You know what I'm saying?
Oh, so where in the galaxy you would find most of the massive stars, you also seem to find these shock waves, these bow shocks.
Yeah, if they're going fast, I would have thought they would have maybe spread out a bit more than they have. That was to me a surprise from our survey paper where we had this distribution of 709 of the bow shocks.
Okay. So let me get to some of Andrew's questions because he's been looking forward to this. I want to make sure I get them all in. Where is his first question? He was way back here. He goes, here it is. Okay, Andrew Planet is asking, is it possible that we could hitch a lift on the gravity of a hypervelocity star on a spacecraft? And is it a good place to look for exospecies because they might have thought of the same thing? What do you think of that idea? Can we hitch a ride on these things somehow?
Will, are you still there or did you freeze?
I'm still here.
Yeah, he's here.
Okay. Well, believe it or not, I've actually thought about stuff like this before. And so these massive stars are so uncommon that, you know, there aren't any really close to us. The picture we showed before is Zeta Ophiuchus, one of the most nearby examples. We're not getting anywhere near it anytime soon. It's hundreds of light years away. You could imagine getting a gravity boost from a star that happened to pass close to the sun if you happen to build the spaceship that you needed, which of course we haven't, and we haven't even drawn up the plans for it. And if that happens, yes, it is possible to use that, but it's much more likely that you encounter a low mass star because they're much more common than these high mass ones.
Unless, of course,
oh,
go ahead.
By the same token, high mass stars, because they don't live a long time, not the place you want to look for ET.
Right.
100 million years, we don't think that's enough time to evolve life. Certainly took longer than that on Earth.
Or even to make exoplanets around them, correct? You don't see, because of the energy and the solar winds, you don't see a lot of planet formation around these stars either.
I guess say we don't know. I think very well, whether there are other planets around these stars or not. There's some models that predict some lower mass stars form around these high mass stars originally. So you could have solar systems of a big blue star surrounded by a bunch of cool red ones.
That's true. Okay.
But we don't know.
Yeah, but if you happen to get one coming closer to the Earth, we might be able to hit your eye. The problem with that is you don't want one of these big massive stars with these big bow shocks heading your way, I can imagine. What would that be like if if this bow shock you just showed us flew by the Earth? Are they dense enough? What's the density in those things? How much stuff is in there? Could it
Gosh, Will, has Chip gotten to the point of measuring that number yet?
We're working on that currently, but I don't think we've got any real definitive numbers on that yet. But they are still relatively sparse, I believe. So
I won't think we'd notice, honestly.
Okay, so that's okay.
I think we'd notice if we got too close to a star that was 100,000 times more powerful than the sun.
Yeah, that effect.
Exactly.
That effect, I think we'd notice. But I was just thinking about the bow shock itself. Would it have any effect on, say, something like our magnetosphere or even the pressure going up against the planet?
It might. It's hard to say. Actually, I have a postdoc here who's thinking about high energy properties of bow shocks, and she's uncovered literature saying that these bow shocks can be particle accelerators, and they actually can generate X-ray, strong X-ray radiation. So depending on how strong that X-ray radiation is, you might not want to get too close.
Good point. Okay, Don, I want to get you in on this a little bit. You are currently studying physics with Dr. Povich, with Matt Povich, and what's your role in this research? Because your name's on the paper. What's your role here? And give us a sense of what it was like to work on it for you.
Right. So originally, for that paper, what I was doing is I was actually loading the Spitzer images and actually looking through the plane of our Milky Way to find these bow shocks. So I was helping find the 709 that were originally on that paper.
So you found all seven? Did you find them all?
No. I didn't find all 700. I found a few, but I came at sort of the tail end of that paper. So I helped find a few, but certainly not all of them.
So it was your job to manually go through the Spitzer images and try to find these bow shocks. What software did you use?
I use DS9 imaging software.
DS9, yeah. That, for those of you who don't know, that is a ubiquitous FITS image server. Most astronomical data are in FITS format. It's a flexible image transport system, and they have these viewers. DS9 is the one that was put out by Smithsonian Astrophysical Observatory, and it's one that almost everybody uses. It's got a lot of tools in there for looking it up. You can download it yourself and get some FITS images yourself as well and play with it if you'd like. So you used DS9. You went through this manually and found a good portion of these things. What was how long did that take you?
It took a good while because in the software the bow shocks are really small in these mosaics, and on top of that you certainly have to change the scaling for especially the 24 micron, which is what the dust brightly glows in. So I could have the image scaled for one thing and catch several bow shocks and then have the others completely not visible at all. So there were several mosaics that we double checked with each other and that I went over several times, and we still missed some. So
yeah, okay. So what do you got up here, Matt?
Well, I was just trying to cue something. You have that picture that Will sent you showing the summer students at Wyoming. Might be a good time to mention the whole team, because this was a lot of data to go through, and Don certainly wasn't the only one to work on it. There's a few other students who are also on that paper. Okay,
I have them up now. Yep, I have them up. So these are other students that are also listed on the paper.
Yep, so this was our 2015 RAU group, the Research Experiences for Undergraduates, that worked with us in the summer of 2015. So these 5 were part of our first wave, and then Don and Daniel were part of our second wave in the summer of 2016.
Great. So this had a large student component to this paper then, didn't it?
Yeah, I've got if you take the picture I'm sharing, now you can see the remaining the next year's students are there.
There's Don way in the back. I see him there. Yeah. Okay, cool. Well, this is really cool. So I'm really glad to hear that you've got the students involved and even got their names on the papers, because this is going to be huge for their degrees and for their getting started in their career. Don, where are you headed next? What are you interested in doing after you get your undergrad in physics?
Well, I'm currently applying to some master's programs.
Well, first let me back up. What year are you in?
This is my senior year.
Oh, you're
so
senior.
Okay. So
you're getting ready to graduate soon. Okay, good. So go ahead. Yeah. So tell me what you're interested in doing.
So I'm applying to some master's programs for astronomy right now, and the plan is for me to do that and hopefully transition to a PhD. And long term, I would like to be a professor and do research and teach others about astronomy.
Yeah, good luck with that. That's a highly competitive thing. I wish you nothing but good luck on that one. Tell us a little bit for a lot of my viewers. My demographics are starting to change a bit. I'm getting a lot of younger people watching. A lot of them are considering going into astronomy for a career. So I did it late in life. I didn't even start my undergrad until I was 30. And I was wondering, what advice would you give to somebody who's thinking of going into astronomy? And based on your experience, what are the best what are the things you've learned to do and not to do while as a physics major?
Well, yeah, a lot of my experience as a physics major, I would think definitely time management is probably the most important thing that I didn't have coming in. That it's very important. Just managing your time, like when to start the homework versus when to study. You have to make time for it because you can't do it all at once. Yeah.
I don't know about Cal Poly, but at University of Colorado, we had to take, and I was grateful for this, classes in other departments like the humanities and English and other, just to kind of, I was so glad to get out of the physics building. I love those classes because you never leave the physics building when you're in there. Were you pretty good at math when you started?
I wouldn't say that. Some classes I was okay in, and others not so much.
Not so much. Yeah,
it was the transition classes I think I struggled the most with.
Okay. All right.
Entirely new branches of mathematics. Yeah.
You've gotten a lot better though.
Yeah.
I'm taking pretty hard classes now.
Yeah.
It gets worse when you're a senior. Oh my gosh. Okay. Well, let's let that be a segue into the citizen science component to this research. So I don't know which one of you want to talk about this, if it's Matt or Will or even Don. You guys have a project, and you're the lead scientist on this, Matt. So I guess we'll start with you. The Milky Way project. What is this thing?
Well, so one thing Don didn't mention is how tedious it is for this group of 6 or 7 students to look through just acres and acres of images. I mean, there's so much real estate you've got to hunt through. You're looking at these pictures, you're panning, you're zooming around, you make it brighter, you make it dimmer. I mean, you're just looking for all these needles and haystacks, right? And so what we always wanted to do, actually, we never actually, Chip and I, intended to have a group of undergrads do this work. We wanted to do it with citizen science, and we just, because there was a bit of overhead in getting the citizen science project going. We had to take a first pass with our own students. But the idea now is so I guess we're sharing our website now. So this is www.milkywayproject.org.
Yeah, I got it up now.
This site has been around since 2010. But what it wasn't doing was looking for bow shocks specifically. We were looking for a related phenomenon called interstellar bubbles in the infrared that are produced by these same kinds of stars. The difference being that for most of the bow shocks, they're moving fast. But the interstellar bubbles are what happens when the star kind of stays put and the wind just goes off in all directions and makes a bubble that's round or maybe a bit broken or something. So we'd been looking for bubbles for a long, long time. We also wanted to look for bow shocks. And this sort of coincided, unfortunately, with me assuming the leadership of the project when the previous PI had to step down and go take a nice job at Google as a programmer. So we had, I told him, when he told me that, I was like, well, sorry to see you go. And if you didn't, I would fly across the ocean and kick your butt myself for not going and taking this job. So we had about a year that I had to work to get this set up again, but we also knew we wanted to find bow shocks sooner than that, and that's why we're doing this project in two stages. All right, so the basic idea is this: you go to the site and you can see that you have a couple different options here, and I guess let's see if I interact with this window, it will work, right? So you can go in, you can say learn more, and it'll tell you. Let's see. Okay, there we go. It'll show you kind of what we're doing and give you some background. You can read all about the science. You can see who's in our collaboration, who's our partners, and things like that. You can learn about the team. You can peruse previous results and all that good stuff. But the most important thing to do is to participate. So when you first go to the main site, you see it says get started. You see some example pictures that people are talking about right now. There's this chat feature where people can discuss what they're seeing in different pictures.
9 people, yeah.
If you scroll down, you can see some statistics, which tells you that we still have a lot left that we want to do by this measure. We currently have 5,000 registered volunteers who have actually logged into the site and created usernames and are using it. There's actually quite a few more who contribute without registering. We have 77,000 images. That's what the subjects are. And we are trying to make over 2 million classifications. And I'll explain what a classification is in a second. So,
can I just real quickly interject to you, folks? I put the link to this in the description box of this Hangout. Click on it and you can follow along as well.
Yeah, and I wanted to emphasize also that for all these type of projects, the Zooniverse, they're called Zooniverse type, you don't have to register. You can do it as a guest, but I think it's a lot more fun because I know Matthew and colleagues are going to talk about the chat feature and how to interact with other people who are working on the data. And so it's really worth registering for it. I know it sometimes seems like a pain, but I registered, so and I've done some classification of bubbles. So anyway.
Okay.
Give that.
Oh, thanks for that, Carol. Yes, and indeed, one thing we really always like to do is give credit to all of our volunteers, all these thousands of people. They're making data for us. We write papers using that data. If someone doesn't sign in, we don't have their name. We can't credit them on the paper, and we want to credit everybody. There will be a table associated with our next paper that lists all of the username handles of all the volunteers who contributed to it.
Yeah, you can see up here, this is part of the Zooniverse URL, so you can see that it's it's dovetailed into a lot of things. So you guys need to go there and help out. What is it? So the fact that just finding these bow shocks is extremely challenging, and you had Don spend a good part of a semester doing it, or even longer. I'm not quite sure how long, but the problem with big data, folks, and this is what we're talking about here, there's a lot of data, a lot of it, just gigabytes, terabytes, petabytes of data coming off of telescopes now that simply can't be looked at individually. And many things use automatic software to find things like stars versus galaxies. But it's hard to really, these diffuse objects, it's extremely difficult. Extended objects like nebulae, extremely hard for an automatic program to do. So it's great that we can get the public involved. And there was a person who got, one of the very first Zooniverse projects, somebody discovered a brand new kind of galaxy. I mean, it was called a Vorwerp or something like that. And she became quite famous for it. It was named after her and everything else. So it's really worth it if you've got time and the interest to go through these data sets. And sign up. So and it's important to sign up so you can get credit for it too. So is there anything else you want to say about this Matt?
Oh yeah, I
wanted to say some more because I want to hear about classifications and how an object is done. Because
do you want to drive it, or should I just
those metrics were?
Yeah, I can do that. Hold on.
Okay, why don't you put it up and drive it? And while you're doing that, I'm just going to read a couple of comments. John Suffel is from Hull, England. I want to welcome you. It's good to see you here. Let's see, Charlie Lavender. Tony been a space fan since Space Fan News #1. You're pretty hardcore. Thank you for being here. A couple people here for the first time. Philip Hoffner, Andrew saying hi to Carol.
Hi. Can you mention, like, if you want to get alert? I know our like Andrew and others come back all the time, which is great. We love to have you back, but some people would like to know how do you get notifications?
Okay, so
for the Hangouts is one thing we haven't talked.
Yeah, and we're getting better at this. The best way, and I haven't used it yet, is with my newsletter. If you go to deepastronomy.com, sign up for the newsletter, that's going to be a main event. I'm looking into paying for a service that if you text a certain thing, you can get texts you can get alert texts from this service if you opt in, but that costs money and I haven't set it up yet. So the best way to find out about these Hangouts is, first of all, no, it's every Thursday, 3 o'clock, you need to be here. We're doing something every single Thursday right here at 3 o'clock Eastern time. The topic, though, will be listed on deepastronomy.com/live, as well as I'm going to be sending out newsletters with the calendar. Now, Carol's great about this. She's good about scheduling things way far in advance. Harley, not so much. I don't usually know what the Hangout's about until the Monday before it starts. So while you know there'll be a Hangout on that Thursday, you won't necessarily know what it is. So that's a good way to find out about it. Okay, Matt, go ahead. I got you big.
All right. Okay, great. Let me make me big too so I can see what I'm doing on there. Hello, there we go. All right, so if you're back on where we start on this homepage, if you go into Get Started, and there's two options. There's Learning the Ropes and Map the Milky Way. Map the Milky Way is the main event, but I'll show you the Learning the Ropes because that's where people go and get trained on specific images. So if I click on that, you get taken into our classification interface. And this will say already seen because, of course, I've already seen it, right? I'm logged in as me, and I've looked at this all the time. What we're seeing in this image, actually, this is a great one to start with, and I won't even have to show you any others because I think Don would agree. Everything we might want to talk about is in this image. So in this image, I actually see a beautiful example of a bubble, and it's also got a bow shock nestled up right next to it, all right? So here's how I'll show you that. You'll notice that I have this bubble tool highlighted in blue. So if I go onto the image, I can draw out an ellipse and fit it to the inside of this bubble. And the bubble is the green ring here. It's got kind of a red center, but it's a green ring. That's what we're interested in. So I can go and kind of fit this here. Pay no attention to this bright thing over here. We're not actually interested in that. And people always like to click on the bright stuff, but that's not something we're looking for. I do see something.
This is not the bubble you are looking for.
Exactly, yes. This is not the explosion. I don't know what that is, but yeah, it's a bright star. Now, there is a bow shock too. And if I want to highlight that, I have to click on the bow shock tool. So I do that. And this is tricky because it's really small, but I'm going to do my best. And so I click, 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 and close the thing up. And I've sort of made a triangle around it. And I can actually bend the edges of the triangle. This is called a Bezier tool. I didn't know that word until I learned it through the Zooniverse. And I can kind of bend this banana around and fit it to the shape of the shock. And so that's all well and good. But Don, do I really care about the banana?
No, not at all. You care about the driving star.
Yes, I care about the star here. Okay, the banana is something that's good to do, so we know that you're being honest and that you found a bow shock. But if you don't then go click down here and say, I see a star right in the middle, and I do, it's this one right here, put a little crosshair on that, then I can say, I'm done. I've made my classification. I found one bubble, I found a bow shock, and its little driving star. I can also look for some other things. I mean, there probably are other things in here. We're looking for something called a yellow ball. I actually see something here that I might call a yellow ball, so why don't I mark that? But actually, my bubble's in the way, so I'll hide my previous marks. Why is that not working? Well, it's supposed to work, not working.
Because it's a demo on.
Because it's a live demo.
It's a live demo is why it doesn't work.
Yeah, so I would like to mark this other thing as a yellow ball. Everything seems kind of frozen. Oh, okay, it worked. Okay, it's gone. So now I can mark this with a little circle. It's a yellow ball. It's yellow and it's shaped like a ball. We are interested in those, so I'll mark that one. All right, now I'll get my marks back if I can. and
I'm
show
sorry,
everything at the end.
why are you interested in yellow balls?
Yellow balls we think are baby bubbles that
Ah,
haven't broken out yet.
okay.
That's what we think they are. We have some team members who are very interested in whether these yellow balls are baby bubbles or they're just less powerful bubbles, and we think that there's something like the bubble phenomenon. Okay, so I think I've broken this, and I'm not going to see any of my marks anymore, but that's okay. Hopefully everybody's got the idea. If you're done, you click done, and you say, okay, this is all well and good. I'm not going to click done because I don't think it worked. But here's some other things. Suppose you don't know what the heck you're doing. You can say, show me the project tutorial down here. And this will actually give you a full walkthrough of the different kinds of things that we are looking for. Let's look at bow shocks. This is a bow shock, and it tells you what a bow shock is. And there's this nice little animated GIF to illustrate how you do that drawing that I was just doing, right? How you can adjust things around and find it. And then once you found the bow shock, you have to find the star, and there it is. Right. And so we're going through 77,000 really different postage stamp images like this one, and looking for everything we can find in each one.
And these are primary infrared, right? You said?
These are all infrared. That is correct.
Okay. Go to bubble. What's a bubble?
A bubble is a place where you've got one or more of these massive OMB type stars. It just formed out of some dark, dense cloud, and it's lit itself up, starts dumping energy out, and it actually, through the combination of its winds and honestly just heating up the medium, it creates an expanding bubble, like a hot air balloon.
How big is
and
that?
That pushes everything to the side, and you get this green ring where everything is pushed off to the side, and everything in that ring is glowing brightly because the ultraviolet radiation from the stars is exciting these organic molecules called PAHs, polycyclic organic hydrocarbons.
So is it a bubble or a ring?
That's an open question. People have argued about whether the bubbles are really closed spheres or whether they're really more rings. I think it depends. Sometimes they're broken and they just look like little arcs. But it always looks kind of like a ring or an oval.
Because I was wondering before when you were speaking, as any one of you was speaking of what you're looking, mostly we associate the morphology of seeing the kind of, edge on, if you will, where it's transverse to what we're looking at, sort of, more or less. Do we know what they look like if they were coming at us? Oh,
you're talking about the bow shock, I think.
Yeah.
Right?
Well, I was talking about both rings and bow shock.
Right. Well, yeah, the fact that we see so many bubbles that look like rings and some of them are stretched, but we don't see very many that are stretched beyond an aspect of 2 to 1. I think that would tend to disfavor a full-on ring scenario because I think we'd see more of them that are very, very stretched out than we do. But the bow shocks, this is a really good point. We couldn't really identify a bow shock very well. It was coming straight at us. It might just look like a star with a little halo of red around it. It might not look like very much.
Yeah, a lot of this morphology seems to be sort of line of sight dependent.
Welcome to astronomy.
Yeah.
If only we could walk around and see stuff from the other side, we would know.
I know. I recently downloaded Space Engine, and I've been kind of spoiled because you can go anywhere in the universe and look at it up close really fast. So that was kind of it's really, you're right. We can't just do that in real life. Hans Milling, welcome back to the chat room. He's asking, so how fast are the stars moving? I think you said between 100 and 200 kilometers per second, right?
Or some of them could be a little slower, like 50.
Yeah.
Okay, so 50. And it goes, is it relative to other stars the same area or relative to Earth? What's the speed relative to?
I think this would be a great time for Will to talk about how these stars even get moving so fast in the first place.
Okay, Will?
Sure, I'd be happy to jump in on that. So as you can imagine, stars being rather large and massive, it takes a lot of energy to get something like that moving. And we basically have two basic mechanisms for how this could work. The first is whenever stars form, they form in these clusters of stars. So you don't just get one or two stars at a time. You typically get a dozen, a couple dozen, maybe even hundreds of stars if there's enough gas and material there. And what can happen is if a star gets too close to its neighbors, it can actually get slingshotted out of the cluster, similar to what we do with our satellites, where we make close approaches to the Earth or Venus to fling them towards Mars or out into the outer solar system. So that's one mechanism. The other would be where you have two stars that actually form as a binary pair. So they're orbiting each other, and the more massive of the two stars will actually explode in a supernova. And what will happen is if that's asymmetric in just the right way, where most of the energy starts going towards the other star, it'll actually propel that star away from the cluster. And that'll get you up to these speeds that we call runaway stars, where they're moving at 30, 50, 80 kilometers per second relative to the stars and gas around them. So what's most important about these is not their absolute speed, but the speed relative to all the stuff around it.
Yeah, and there's an important linkage between the bow shocks and the bubbles. The bubbles are the birthplaces of these stars. So when they're running away, these clusters that Will is talking about, these are the things that we expect to find inside the bubbles. But once a massive star becomes a runaway, it should escape, and it's gone. And one important test is to see that for the runaway stars, they don't have clusters of little stars associated with them.
Okay, and Hans is also asking, if they're moving very fast, these stars are moving very fast, can you take photos over time to make an animation? I mean, we've seen things like with Eta Carina, we've seen animations of expanding gas clouds. Can you do that with these stars? Are they moving that fast? Maybe take the time series of them and see maybe their proper motions?
The majority of these stars are far enough away that at the speeds that they're moving, it would probably be a pretty boring animation. But for the fastest stars, the stars that we call hypervelocity stars, the ones that are moving 100-200 kilometers per second, those you can definitely noticeably see even over a 5 or 10-year time scale, and you can see some of those animations. But for the majority of these stars that are powering these bow shocks, we're just going to need long enough time scales before that becomes an interesting animation that we're talking probably 30, 50, even 100 years before that really becomes noticeable.
Awesome. That's a good question, Hans. Okay, so, and finally he's asking, and this is in reference to the citizen science sort of initiatives, instead of having people looking at and finding these things, have you looked at using machine learning AI to go through all these photos? Is there any kind of, is there a way to automate this?
Yes. I mean, well, there's a way. The question is whether it's as good or not. It's been done. There's actually a paper by one of our Milky Way project team members, Chris Beaumont. I think that was in 2012 or 2013. Did machine learning algorithms to test, finding out bubbles only. We haven't tried it for bow shocks yet. My philosophy is that we ought to try both. We should always try to do both because the best science is done with multiple independent methods. Machine learning can be efficient and hopefully very reproducible, but large numbers of people working together is also reproducible because, one person, you can't predict what one person's going to do, but you get enough people together in a systematic way, then yeah, you can reproduce the results. And we're doing that experiment right now. We're doing a second pass through the Milky Way project. We've already published a bubbles catalog, but so we're doing a new one and we're hoping to improve upon it. In fact, we know we will. We've already seen enough to know we're improving on previous results. The bow shocks catalog from Citizen Science will be a brand new thing. We haven't done that before. The other thing I just like to remind everyone is that, robots don't pay taxes. We don't do science for robots. Robots do science for us. At least we hope that's the way it works. And the engagement of people in the process of doing science has benefits to society that are hard to measure.
Good point. Well said. Okay, Andrew Planet is asking, is going back to that image you showed of the bow shock and the ship, the analogy that you had made. He's asking, is the gravitational field of the star a more correct analogy of a ship? And Rational Martian, who's also back, welcome back. He comments, not really, Andrew. This is the solar wind. It speeds out all around the sphere of the star. It is just the gas and dust cloud that's being pushed there. So is that pretty much right? I mean, it's not the gravitational field of the star so much, it's the solar wind of that star, stellar wind?
I think, how do we unpack that question? I didn't catch all of it.
Okay, so on the one hand, Andrew's asking, is the gravitational field of the star a better analogy for the ship itself, or is it the solar wind?
The solar wind. definitely. Yeah. So the wind is actually what's creating the arc, the thing that's glowing in the red.
Okay.
The gravity is not, not nearly as important in that.
Okay, so Rational Martian's also commenting, this is a massive runaway. I'm suspecting blue star. That's right, they are blue stars. They run through their fuel much quicker and more violently the more massive they are. Very true. We talked about that, I think, before you arrived. But yes, it is absolutely right, Rational Martian. So the solar wind is more violent. That's also true. Day Lou is asking, could they be dragging planets along? We talked about that briefly, but why don't you answer that, maybe one of you?
Goodness, that's really a great question. And yeah, I guess, the short answer is maybe, but probably not. And even if they are not planets you would like to visit.
Yeah. They almost certainly won't be in a habitable zone anywhere, for sure.
Yeah, how much do we actually know about really massive stars and the existence of planets?
I think we know essentially nothing because most of these stars are so far away. Remember, the difficulty in finding planets around other stars is that the planets are really dim and the stars are bright. This is already a big problem for stars like the sun. So, okay, go ahead and make the sun 100,000 times brighter. You've just made your problem 100,000 times worse.
That's an excellent point. It's easier to find it around these smaller stars. Komodo Dragon Yem is asking, does the effect like bow shocks apply on comets if they are traveling through our own solar system? In other words, would they, as a comet as it travels through our solar system, would it also have a bow shock?
Absolutely.
Good question. Let's see. George Caldwell, do massive and fast-moving stars ever produce black holes that themselves are fast-moving as a consequence? And at that, would these black holes radiate Hawking radiation at a faster rate than standard? Let's parse that up into the first part. So these massive stars are going to die, presumably in a supernova, or if they're big enough. Would they produce a black hole that would also then be moving that quickly?
That's a great question and something we're kind of looking into. Part of the reason we're looking at these bow shock stars is to measure how much mass these stars are losing, because you need to have a certain amount of mass at the end of your lifetime to produce a black hole. So the question is whether those 8 or 10 solar mass stars that we're seeing now will have enough mass to generate a black hole. Obviously, the very largest of them will definitely have enough mass, and they will produce a black hole at the end of their lifetime.
Okay, and Eurico Roberto, is this an Astro Coffee hangout? I forgot again to say, you are watching an Afternoon Astronomy Coffee hangout. My name is Tony Darnell, and my guests are Dr. Matthew Povich. He's a lead scientist of the Milky Way project, and he's the assistant professor of physics and astronomy at California State Polytechnic. Right next to him is an undergraduate student, Don Dixon, who worked with him, gathered a lot of these bow shocks for the paper that we were talking about today. And also joining me is Will Chick. He's a grad student at the University of Wyoming, who's also an author on this paper. And we're discussing bow shocks and fast-moving stars. I can't wait to get my lower thirds back. So because I always forget that. Thank you, Eurico. And so the second part of George Caldwell's question, would they radiate Hawking radiation at a faster rate than standard? Do you guys know that? No, I don't either.
I don't see why.
I can't. It's not my expertise, but I can't think of why that would be the case, because that's not created by interactions with matter from the outside. That's spontaneous pair production, quantum mechanical effect. It probably doesn't care too much, whether about the interstellar medium or anything like that.
Yeah, and Hans Milling is also saying that he read an article that this is going back to your comment about how quickly life can form on some of these planets. They found evidence of life in a cave in Canada that suggests that life might have evolved just after 300 million years. So perhaps ET is possible on a planet around such a star. So
that's still too long.
Yeah,
they don't last that long.
Yeah, that would be the very smallest of the stars that we're talking about here. If
not even. Yeah.
Okay, and I'm just going through George Caldwell is commenting. This is in reply to, I think, with our discussion with Don. My current goals are going into astrophysics and hopefully going down the PhD and professor route. So I'll take on board any advice. Okay, we've got a grad student here who's trying to do that, and we've got an assistant professor who's done it. So how about some advice, guys? people on the track to going what you're doing?
Go ahead, Will.
I would say if you want to work your way into graduate school, of course, making sure that you're doing well in your math and physics classes is definitely going to be a huge plus. But what's most important is developing relationships with the professors around you, making sure you get involved with research as early as you can.
Like Don is doing.
As Don is doing. Don is exactly on the right path to making sure things like these REU programs, these research experiences for undergraduates, are great places to get that kind of practical experience, and really just make sure that get involved as much as you can. And other than that, it's hit those books hard and keep at it. Even if you don't succeed the first time, sometimes it takes a couple rounds of applications to make it into the graduate system.
So what's graduate student life like? What's a day for you like?
Well, at this point, I am finished with all of my classwork. The first couple years of graduate school looks an awful lot like the senior year of your undergraduate experience. A lot of classes and then trying to dip your toes into research. At this point, I'm more or less on my own as far as the research under my advisor. So it's a lot of coming in, reading through the recent research, and then trying to parse out what my next project is. So whether that's trying to plan out observations to be done either by myself or at larger telescopes, or writing up that research. So.
Right. So a couple of comments here for me. I just want to say that the getting your name on a paper like Don has done, and also as Will's done, is huge in going into applying for graduate programs. And maybe Carol, you could comment too. These things are really important to have on your academic resume. And what Don was referring to also, when you go into grad school, the first couple of years, you have to take a test. I think it's called your comps, right? Your comprehensive test. Is that right, Don? Will? So getting those out of the way and doing well on them is a huge stressor. And then once you've got that out of the way, you can focus on your research. So how long do you think, Will, it's going to take for you to get through the next phase?
I believe that I could, if I wanted to, be done in another 3 years. I'm halfway through my third year now, but I'm planning on doing a sixth year for mine just to make sure that I can get in, take advantage of the resources here as much as possible before making that leap into the great unknown, whether that's postdoc or working as a adjunct professor or whatever that next step will be.
Do you have an advisor right now?
Yes, I do. I work under Chip Kolbenicki, who's the lead author on this paper.
That's right. He was the lead author on the paper. Good. Well, how important do you think that is? You're finding the right advisor.
The advisor relationship is absolutely critical. A bad relationship with an advisor can make graduate school feel 10 times longer and 100 times harder. So making sure that you've got a good working relationship with your advisor, that you find somebody who, honestly, it's more important to find a personality and work you mesh well with than somebody who's doing exactly what you want to be doing.
Any comments, Matt?
He's absolutely right about that. I mean, it's like any other profession. It's the relationships you build with other people that ultimately ensure your success. You need supportive mentors, you need dedicated teachers, you need people who are, when you're a junior scientist or a student, you need people who will help you and not compete with you or undermine you. You need people who can connect you with opportunities that other people have. I mean, that's what happened with Don. Don got the opportunity to spend a summer working with Will and Chip and the other students at Wyoming because Chip and I knew each other, and I'm able to connect him to one of my colleagues.
Yep, that's a good point. Okay, well, one more question from Hans Milling. Does US 708, I guess that's a designate for a star, still hold the speed record for the fastest moving star with 4.2 billion kilometers per hour? I've never heard of this.
As far as I know, that is still the fastest hypervelocity star that we have found, yes.
Oh, that's a hypervelocity star.
Yes, so that's one of those that's going, I think it's close to 2,000 kilometers per second, but you might need to check me on that.
Okay.
One thing we should have mentioned that I think we failed to is that the sun's speed around the center of the galaxy is 220 kilometers per second.
We did fail to mention.
Yeah.
So all of the
it's not-
stars are
not
moving
silly.
along at 200 some odd
Yeah.
kilometers per second. That's the regular orbit. So we're really talking about deviations from this. That's what we mean when we say runaway stars. That they're running away. They're maybe everyone's driving down the freeway, but someone's decided to slam on the brakes, right? Well, that's a pretty dramatic event, right? Or just someone goes the wrong way down the highway at the same speed limit. That's going to be a pretty dramatic thing.
Yeah. So Hans, that goes back to your earlier question about relative to what. So there you go. Okay. So a couple quick comments. Googleplex is saying a lot of study and of course a deep interest in the subject is key to getting your PhD. Best of luck. George Caldwell saying I live in Cambridge, so the science centers here give really good opportunities. I was also considering theoretical quantum physics because the maths seem really interesting. Wow, good luck with that, George. I wouldn't be able to do that.
That's one word for it. Interesting.
Interesting, right? Okay, well, and finally, Rational Martian. I wish I had done something really interesting. I do-ish. I do-ish, but not on the order of actual science and breakthrough stuff. I'm an engineer. Hey, I'm an engineer too. Okay, don't knock being an engineer. I'm a software engineer though.
Oh my God, that explains a lot.
All right. Okay, folks. Well, that is it. I'm going to have to cut it off here because we're out of time. This has been a really great hangout. Thank you, Carol, for putting this together. We've been talking about fast-moving stars and bow shocks. Go sign up for the Milky Way project.
Absolutely.
And go help these guys out. Get some classifications done. Help them reach 1 million. And help them get these guys done. It really is. You can make a real difference here, folks. This is like the golden age of astronomy, but you get to work with actual real data with and collaborate with and do real science. So please help these guys out. Go in there and do it. I want to thank my guests. Dr. Matt Povich, he's the lead scientist of the Milky Way Project, and he's the assistant professor also of physics and astronomy at Cal State Polytechnic University in Pomona. He's got a graduate student, Don Dixon, right next to him. Thank you, Don. Thanks for giving us your insights and what it was like to work on this paper. Will Chick, he's studying, he's a PhD grad student at the University of Wyoming. Real quickly, I know I'm out of time, but real quickly, what's next for you guys? What's the next phase of this research? Is it to get all the classifications on Milky Way project, or is there a next step?
I mean, the important phase is what Will and Chip are doing, I would say, or the science.
Okay.
Yep. So the phase that we're working on right now is actually trying to quantify the material that's in those nebulae right now. If we can figure out how much material the stars are supporting, that'll give us an idea of exactly how much of that stellar wind is necessary. So how much mass those stars are losing. So that's really where my section of the research is going right now.
Yeah. Okay. Well, good. Well, I hope that as you guys make progress, you'll consider coming back and talking more. When you get some more papers written, we'd like to come and discuss them. So thank you for taking time out. Carol, thanks for putting this together. This has been an awesome hangout. Really appreciate it.
Yeah, it was great.
Yeah.
Really good to hear about it. And I've always been fascinated by the Milky Way project. I did play with it a little bit, and it was good to talk to you. It was great. And sorry that Chip couldn't make it.
I know. Well, maybe next time. And you
He was very gracious about it.
in a lot of citizen science things too, as well. You were so
have.
this is one of many.
Yes.
Awesome. Okay. Well, on behalf of Carol Christian and my guests, I want to thank you all very much for watching. Tune in next week where we got our Future in Space hangout. Topic is, but it's going to be great. It'll be next Thursday at 3 o'clock. That's how you know. Always same spot, same time every week. So come join us, and we will talk to you then. As always, keep looking up.
Looking up.